Welcome to my lecture on the hypergeometric distribution. So this is something that we've actually dealt with in chapter 1 and that we're just going to revisit. So let's just briefly talk about the random variable that's involved here. So in order to do that, I need to give you a quick example. So suppose in a shipment of parts, and there are 20 parts. There are 8 defective. Included in the shipment. So I just want to be clear here that there's a total of 20 parts and 8 of the 20 are defective. Okay. Now these parts are going to be installed in a device, okay, and the number of parts installed that are defective is the random variable, okay, and I should say that only 7 parts, so 7 of these parts will be installed. Now I should say that the defective and working parts are indistinguishable. Like, you can't tell them apart. They're not obviously broken versus working. So note working versus defective are indistinguishable. Okay, and that went off the screen a little bit. So now let's write down the random variable. So here, X, this is the number of defective parts installed. Now notice X is not binomial. And it's not binomial because there's not a fixed probability given. Okay. Now you might be tempted to say, hey, the probability is going to be 8 out of 20. But if I pull one defective part, the probability for my next defective part would then be 7 out of 19. So that probability is always changing. It's not fixed. And that indicates that these are not independent events. Okay, so I just want to write that down because this would be the distribution that most people would confuse the hypergeometric with is the binomial. So I wanted to also state that the values that x could take on, they're random. It could be 0 defective parts installed, it could be 1 defective parts, 2 defective parts, right? All the way up to, well, we have a sample size of 7, it could be 7 defective parts. So also we sample m equals to 7 parts. Okay, so now let's work out the solution here. I want to calculate the probability that there are 4 parts installed. Okay, and so I'm going to do this. Probability x equals 4. That's what we're asked to calculate. Well, this is the number of ways x equals 4 occurs, going back to chapter 1. Divided by the total number of outcomes. Now, let's think about the denominator. The total number of outcomes is that we're installing 7 parts. Okay, and I'm installing 7 parts out of 20. So all I need to do is sample 7 parts out of 20. It doesn't matter whether they're the first part installed or the last part installed. They're included in the sample. That tells me order doesn't matter. So I'm going to have 20 choose 7. Okay, and I'm going to note here, order does not matter. Okay. So if I install 4 defective parts, so it's going to be the number of ways to install 4 defective times, well, if I install 4 defective, that leaves 3 parts that need to be installed, and neither of those 3 parts can be defective, so they have to be working. So I need a total of 7 parts, 4 of them defective, 3 of them working. So times the number of ways to install 3 working. Okay, and again, order doesn't matter in this situation. I have 8 defective and I need 4 of them. I have 12 working and I need to select 3 of them, and I have 20 total and I'm just pulling 7. When I do this calculation, I'm going to get 0.199, so about a 20% chance that 4 defective parts would be installed. Okay. Now let's go ahead and discuss this in a little bit more detail. Okay. So that was the hypergeometric, that was the hypergeometric distribution. And let's talk about that, what went on in that problem. So if I wanted to abstract this problem, we're going to take a sample of a population of size m. In this case, m was 7. Okay. There is a subset of the population, okay, with a characteristic. And that characteristic was that they were broken. And I'm going to call that R. Okay. And my random variable x is going to be the number of individuals or units sampled with the characteristic. And in this case, I can write down probability x equals little x. So the way we calculate probabilities is, well, I need to write down one more thing. So before I back up and write down the probability, I need to know here this one thing. So I need to know the population size. I'm going to call the population size n. Okay? And now we're ready to write down the probability distribution function. Okay, so if I want to know the probability that there are x individuals with the characteristic, well, the population size, including the characteristic, is going to be n, and I'm going to choose n of them. Okay, now I want to obtain x of these individuals with the characteristic. There are a total r of them with the characteristic. So let me make that a better r. And I'm going to select x of them. Now, there are n minus r individuals without the characteristic. And I'm going to have the remaining of my sample. I have a sample of size m, and I want x of them to have the characteristic. But the remaining of them is going to be m minus x without the characteristic. Okay? So now, this is how we calculate probabilities with the hypergeometric. This is the density function. And that's how we compute probabilities. This density function has a mean value, e of x, and this is going to be calculated as m times r over n. So m is your sample size, r is the number of individuals with the characteristic, and n is your population size. Okay. All right, so let's do one more example here. Okay. Now, when I calculate these probabilities, I actually don't use the density function formula. I just think through it, and it always just comes to my mind. Okay. So the CDC is sampling a small community of 100 individuals. Of these 100 individuals, 30 of them have been infected with a virus. Okay? And the CDC is going to take a sample takes a sample of 12 individuals. Okay. What is the probability that exactly 5 individuals have the virus or disease? Okay. And so we're going to be asked to calculate probability x equals 5. Well, in this population, there's 100 individuals. 12 of them are being sampled. Okay. Now, in the numerator, I want 5 successes. Okay. So 5 successes out of, well, there's 30 individuals to select from. So 30 choose 5. Now, if there are 5 successes, that means that there needs to be 7 failures or 7 without the virus. So I'm going to do 7 because 7 plus 5 adds up to 12. And that leaves 70 individuals to select from. And that's the probability. So let's run that in my calculator real quick. So 30. And the odds are going to be 0.163 or about 16%. Okay. Now, there is a different scenario here. One in which you could ask this question. What are the odds there are 5 or fewer individuals with the virus? And that would be asking you to calculate probability there are 5 or fewer, so we could include a 5. So that'd be probability x is less than or equal to 5. And this would be probability x equals 5 plus the probability x equals 4. And we keep going all the way down to the probability x equals 0. So we'd have to add up all those probabilities. And I'm just going to write out the first and the last term. So you'd have to add up this probability that there would be 30, choose 5, times 70, choose 7, divided by 100, choose 12. That would be the probability x equals 5. Then you have to add up x equals 4, x equals 3, x equals 2, x equals 1, and you keep going all the way down to the probability x is 0. Well, if x is 0, that'd be 30, choose 0, times 70, choose 12, divided by 100, choose 12. And that'd be a bunch of probabilities to add up. It's a pain. I'm using a computer to calculate this, and I'll show you in R in a different lecture how to do that. So if I did my R correctly, you're going to get this value. Just a second. So that would be an 89.6% chance, if I did my R correctly, that you'll get that number. Okay. Well, thank you for checking in on this lecture. I just have one last note to say, which is the hypergeometric does not have a moment generating function. That's because the series does not converge. Okay. And thank you for watching.